This is Chapter 3, Linear Kinetics, explaining the causes of linear motion. And it's really just an overview of how to explain the causes of linear motion. Here are the objectives for Chapter 3. Explain Newton's three laws of motion. Apply Newton's second law of motion to determine the acceleration of an object if the forces acting on the object are known. Apply Newton's second law of motion to determine the net force acting on an object if the acceleration of the object is known. Define impulse, define momentum, explain the relationship between impulse and momentum, and describe the relationship between mass and weight. So Isaac Newton was an English mathematician, and Newton was a student at Cambridge University and later became a professor there. Many of his ideas about mechanics were actually conceived during a 2-year retreat to his family's estate in Lincolnshire when he was in his early 20s. Newton presented his three laws of motion and his law of gravitation in his book Principia in 1686, and these laws formed the basis for modern mechanics. It is these laws that provide the basis for the sub-branch of mechanics we know as kinetics. Newton's first law of motion is commonly referred to as the law of inertia. Translated directly, this law states that every body continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. This law explains what happens to an object if no external forces act on it, or if the net external force, also known as the resultant of all external forces acting on it, is zero. Newton's first law says that if no external force acts on an object, the object will not move if it wasn't moving to begin with, or it will continue moving at a constant speed in a straight line if it was already moving. So can you think of any situations in which no external forces act on an object in sport? Just kind of consider that. Any situations in which no external forces act on an object in sport. Let's see how Newton's first law of motion applies to human movement in sport. Gravity is an external force that acts on all objects close to the earth. Apparently, there are no situations in sports and human movement in which Newton's first law of motion applies. Would that be true, though? Perhaps we can find applications of Newton's first law in sport if we consider only motions of an object or body in a specific direction. Previously, we analyzed projectile motion. We did this by resolving the motion of the projectile into vertical and horizontal components. Vertically, the velocity of the projectile was constantly changing, and it accelerated downward at 9.81 meters per second squared due to the force of gravity. In the vertical direction, Newton's first law of motion does not apply. However, horizontally, the velocity of the projectile was constant and its acceleration was zero because no horizontal forces acted on the projectile. Remember, air resistance is negligible here. Therefore, in this case, Newton's first law of motion does apply. The net horizontal force acting on the projectile is zero, so the horizontal velocity of the projectile is constant and unchanging. Newton's first law of motion also applies if external forces do act on an object, so long as the sum of those forces is zero. So an object may continue its motion in a straight line or continue its state of rest if the net external force acting on the object is zero. Recall that if the sum of all forces acting on an object is zero, then the object is in a state of static equilibrium. Newton's first law of motion is the basis for static equilibrium. Newton's first law of motion also provides the basis for the principle of conservation of momentum. What is momentum? Linear momentum is the product of an object's mass and its linear velocity. The faster an object moves, the more momentum it has. The larger an object's mass, the more momentum it has. Newton's first law basically states that the velocity of an object is constant if the net force acting on the object is zero. In sports and human movement, most objects we deal with have a constant mass. If the velocity of the object is constant, then its momentum is constant as well, since mass doesn't change. Momentum is constant if the net external force is zero. Since velocity is a vector quantity, momentum is also a vector quantity. The total amount of momentum of an object can be resolved into components, or if the components of momentum are known, the components can then be added together to determine the resultant momentum. Conservation of momentum applies to all dimensions, so x, y, and z. The value of the conservation of momentum principle is more apparent when we are concerned with not just a single object, but a group of objects. The analysis of a system of two or more objects is simplified if all the objects are considered part of one thing, the system. If the objects are considered together as one system, then the forces that the objects exert against each other are internal forces and do not affect the motion of the whole system. Therefore, we don't have to know what they are. Only external forces, forces exerted by the agents external to the system, will change the motion of the system. What happens when two objects with the same mass collide? What about two objects that collide that have different masses? When two objects collide in a head-on collision, their combined momentum is conserved. We can use this principle to predict post-collision movements of the objects in certain situations if we know their masses and their pre-collision velocities. The textbook gives the example of flicking penny A into penny B. When this happens, the velocity of penny A just before the collision equals the velocity of penny B just after collision. For head-on, perfectly elastic collisions of two objects with equal mass, the pre-collision momentum of each object is totally transferred to the other object post-collision. But what happens if the masses of two colliding objects are not equal? Will momentum completely transfer from one object to the other, and vice versa in all perfectly elastic head-on collisions? In a perfectly elastic collision, not only is momentum conserved, but kinetic energy is conserved as well. What if we were to flick a nickel into the penny? In this case, the penny rapidly moves in the same direction as the nickel was before the collision, but the nickel also keeps moving the same direction, although much more slowly. If momentum was transferred completely from the nickel to the penny and vice versa, the nickel would not be moving after the collision. There are examples of perfectly elastic collisions in two dimensions of a moving object with a non-moving object. What happens, though, if both objects in a perfectly elastic collision are moving along the same line but in opposite directions? We must remember that momentum is a vector quantity, so the momentum of each object is opposite to the momentum of the other object in the collision. Imagine flicking both pennies at each other while they strike head-on. Remember, after they collide, they bounce off of each other and move into the opposite direction of their pre-collision velocity. If one is moving faster than the other, then the velocity will be transferred to the other object and vice versa. Remember, in a perfectly elastic collision, the pre-collision momentum is transferred to the other after the collision. What happens if we flick the penny and nickel at each other? Immediately after they collide, they bounce off of each other and move in the opposite direction of their post-collision velocities. If the pre-collision velocity of the penny and the nickel were equal but opposite in direction, then the post-collision velocity of the penny will be faster than its pre-collision velocity, while the post-collision velocity of the nickel will be slower than its pre-collision velocity. Not all collisions are perfectly elastic collisions. The opposite of a perfectly elastic collision is a perfectly inelastic, or what we also refer to as sometimes a plastic collision. In a perfectly plastic collision, momentum is still conserved, but rather than bouncing off of each other, the objects in the collision stay together after the collision and move together with the same velocity. Most collisions in football are examples of plastic collisions. Offensive linemen collide with defensive linemen, linebackers tackle running backs, receivers collide with safeties, etc. In most of these collisions, the two players move together as one following the collision. What happens after these collisions greatly affect the outcome of each play and ultimately the outcome of the game. Suppose an 80 kg football or fullback collides midair with a 100 kg linebacker at the goal line during a goal line stand. Just before the collision, the fullback had a velocity of 6 meters per second toward the goal line, and the linebacker had a velocity of 5 meters per second in the opposite direction. In the collision, if the collision is perfectly inelastic, would the fullback be moving forward and score a touchdown just after the collision, or would the defense win? To determine this, we need to use the equation provided here, which is that for the conservation of momentum for two colliding objects. Substituting the known values for the masses and pre-collision velocities gives us negative 0.6 meters per second. So essentially the fullback won't score. He and the linebacker will be moving away from the goal line with a velocity of 0.6 meters per second. The coefficient of restitution serves as an absolute value of ratio of the velocity of separation to the velocity of approach. The velocity of separation is the difference between the velocities of the two colliding objects just after collision. It describes how fast they were moving away from each other. The velocity of approach, or before impact, is the difference between the velocities of the two colliding objects just before collision. It describes how fast they are moving towards each other. The coefficient of restitution has no units. For perfectly elastic collisions, the coefficient of restitution is 1.0, its maximum value. For perfectly plastic collisions, the coefficient of restitution is 0, its maximum value or its minimum value. The coefficient of restitution is affected by the nature of both objects in the collision. For ball sports, it is most easily measured if the object that the ball collides with is fixed and immovable. So for instance, a basketball coming in contact with the ground. If a ball is dropped from a specific height onto the fixed impact surface, then the height of the rebound and the height of the drop provide enough information for computation of the coefficient of restitution. This is an important measure in most ball sports since the bounciness of a ball and the implement or surface it strikes will greatly affect the outcome of competition. For example, if bats had higher CORs with baseballs, we would have more home runs being hit. This is where we see the rule makers stepping in and providing regulations for sport play in order to ensure the fairness and safety for all players. As an example of the use of COR in sport, let's look at the rules of racquetball. They state that the ball must bounce to a height of 68 to 72 inches if dropped from a height of 100 inches. So what is the range allowed for the values of COR for racquetball according to this rule? The COR equation tells us that the racquetball must be 0.82 and 0.85. The coefficient of restitution of a baseball with a wooden bat is about 0.55. The COR of a tennis ball on the court is about 0.73. Therefore, how the ball bounces is determined by its coefficient of restitution. Newton's first law of motion led us to the conservation of momentum principle in collisions. In the analysis of collisions, we considered two colliding objects to be part of the system, and thus we ignored the force impact, since it was an internal force. When isolating one of the objects involved in the collision, this impact force becomes an external force, and Newton's first law is no longer applicable. What happens when the external forces acting on an object result in a net external force not equal to 0? This question leads us to Newton's second law of motion, law of acceleration. Put simply, this law states that if a net external force is exerted on an object, the object will accelerate in the direction of the net external force, and its acceleration will be directly proportional to the net external force and inversely proportional to its mass. Thus, force is equal mass times acceleration. This equation can also be used for force and acceleration in all three dimensions, x, y, and z. Anytime an object starts, stops, speeds up, slows down, or changes directions, it is accelerating, and a net external force is acting to cause this acceleration. Consider an elevator ride. When standing in the elevator, gravity pulls downward on you with a force equal to your weight. But are any other forces acting on you? What about the reaction force under your feet? The elevator floor exerts a reaction force upward on your feet. If the reaction force is larger than your weight, we feel heavier and the net force acts upward, resulting in an upward acceleration. This is exactly what happens when the elevator speeds up in the upward direction. It accelerates you upward and you feel heavier. If the reaction force is equal to your weight, you feel neither heavier nor lighter, and the net force is zero, resulting in no acceleration, thus moving at a constant speed or standing still. If you in the elevator were already moving upward, you would continue to move upward at a constant velocity. If the reaction force is less than your weight, you feel lighter, and the net force acts downward, resulting in a downward acceleration. This is exactly what happens when the elevator slows down. You decelerate upward, or you slow down in the upward direction, or accelerate downward, and you feel lighter. In sports and human movement, we are often more concerned with the final outcome resulting from external forces acting on an athlete or an object over some duration of time than with the instantaneous acceleration of the athlete or object at some instant during the force application. For example, we tend to want to know how fast the ball was going after the pitcher exerted forces on it during the pitching actions. The impulse produced by a net force acting over some duration of time causes a change in the momentum of the object upon which the net force acts. To change the momentum of an object, either mass or its velocity must change. And in some sports and human movement, we most often see a change in movement or momentum due to a change in velocity. The average net force acting over some time interval will cause a change in momentum of an object. We can interpret change in momentum to mean change in velocity, since in human movement most masses are constant. If we want to change the velocity of an object, we can produce a larger change in velocity by having a larger average net force act on the object, or by increasing the time during which the net force acts. The task in many sports skills is to cause a larger change in the velocity of something. Most objects we implement in sport have no velocity at the beginning of the movement, and then after we have applied some external force, the kinetic energy is transferred to that object and it then has velocity. So which is the greater limitation on impulse, the force or the time? When throwing a very light object, the limiting factor is technique. More specifically, the duration of time during which one can exert force on a very light ball is constrained. The ball speeds up so quickly that the hand has a difficult time keeping up with it and still exerting force. On the other hand, when trying to throw a very heavy object, the limiting factor is strength, not technique. The limiting factor is not duration of force application, rather the size of the force itself. The force exerted is definitely larger than that exerted on a lighter object, but the amount of force is constrained by strength. If one is stronger, the force he or she could exert on the object or on the heavy object could be larger, and thus the object would have gone farther and faster. Let's look at an instance when we want to decrease velocity to slow or zero final velocity. A situation where we want to decrease momentum, essentially. How might the impact forces differ if you land from a jump stiff-legged versus with flexed knees? When landing stiff-legged, the impact time would be much smaller and the average impact force would be much greater because the change in the momentum would still be the same. When looking at the right side of the equation, everything stays the same regardless of how you land. Your mass is constant and your final velocity is the same for both conditions. But how can the average impact forces differ between conditions? The change in momentum is the same for the two landing techniques, which means the impulse, or the sum of the forces times the change in time, is the same for both or for the two techniques. However, this doesn't mean that the average impact force, or the sum of the average force, is the same for both conditions, or that the impact time, also known as the change of time, must be the same. If the impact time is short, the average impact force must be large. If the impact time is long, the average impact force must be small. As long as the change in momentum is the same for both activities, changes in impact time are accompanied by inversely proportional changes in average impact force. Moving to Newton's third law of motion, law of action-reaction, we see that if an object exerts a force on another object, the other object exerts the same force on the first object, but in the opposite direction. Let's consider an example. What happens when you are lined up opposite an NFL offensive lineman? When you push against him, he pushes against you. Who pushes harder? Newton's third law tells us that the force he pushes against you is exactly equal to the force you push against him. However, this law doesn't tell us anything about the effects of those forces. If we think back to Newton's second law of motion, we are reminded that the effect of a force on a body is dependent on the mass of the body and the other forces acting on the body. The larger the mass, the smaller the effect. The smaller the mass, the larger the effect. Because his mass is so large and the friction force between his feet and the ground is probably large as well, the effect on your pushing force on him will be small. On the other hand, because your mass is small and the friction force beneath your feet is probably less than that of his, the effects of his pushing force on you will be greater. So, to summarize, Newton's first law states that if no external force acts on an object, that object will not move if it wasn't moving to begin with, or it will continue moving at a constant speed in a straight line if it was already moving. His second law states that if a net external force is exerted on an object, the object will accelerate in the direction of the net external force, and its acceleration will be proportional to the net external force and inversely proportional to its mass. Lastly, his third law states that if an object exerts a force on another object, the other object exerts the same force on the first object, but in the opposite direction. Again, tying back into action-reaction. And that completes chapter 3.